In the previous beta reduction example, we have seen that at some point we're done with computing. We're done with beta abstraction. We can reduce no more. We have reached a normal form. And this is a very important concept. A normal form is an expression that just contains no abstraction, that means no lambdas. And we say that a function or an expression terminates, its reduction terminates if it reaches a normal form. That means exactly the same as termination of any computer program. No more expressions can be evaluated. This termination concept is very, very important for the lambda calculus and programming as a whole. Of course, where there is termination, you could also ask the question whether there are lambda terms that do not terminate. For example, you can evaluate the following term: lambda x fxx applied to lambda x fxx. Pause the video, grab a piece of paper and a pencil and try to evaluate this function for a few steps. You will find out that there are also non-terminating lambda abstractions, just as there are non-terminating programs. Another question that might pop up: can I do recursion in the lambda calculus? And the answer is yes, you can. It's probably not straightforward to see that you can, because for recursion you have to call the function name again inside a function. However, lambda functions are anonymous, they have no names. How would you call the function name again if the function has no name? The solution to this is something called the Y combinator. The Y combinator is just Y, a shortcut for the following rather lengthy lambda term. Lambda f goes to lambda x goes to fxx applied to lambda x fxx. So why does this work? Why is this the same as recursion? You can have a try. Try to evaluate the following function. The function fac, which is the term y lambda f goes to lambda n goes to if n equals 0 then 1, else n times f n minus 1. Try to evaluate fac2, for instance, and see what happens. As if you have evaluated the term that I've shown you before, you will have seen that this term does not terminate. You can reduce it forever. And one very important part here is the order of evaluation. This means that what if there is more than one lambda in an expression, as it is with this term here, which lambda should we evaluate first? Does it matter? Does it not matter? Surprisingly, it matters. The first expression has no normal form. You can evaluate it forever. But the other one has a normal form. Look at the following term. Lambda x goes to 42 applied to lambda x xx lambda x xx. Depending on which lambda of the three you evaluate first, you can either reach a normal form or you can have an infinite reduction. How does it work? Try to figure it out. Try to reduce this term on paper and see if you can come up with a normal form. We now come to the last part of today's talk, which is confluence. I have mentioned before that the order of evaluation, that means which lambda do I reduce first and which one last, is important for the termination of a program. But what if the reduction in program terminates? Let's take that for granted for now. Does the order of evaluation also influence the result? This is important. This is an important question for the lambda calculus and all programming languages in total. Do I get different results if I evaluate certain lambdas first? Because in the example before, I either got a result or I got non-termination. Now, let's see if I can get two different results. If we consider two possible reductions of 2 plus 4 times 3 plus 4, then we can first evaluate 2 plus 4 and multiply this by the result of 3 plus 4, which is 7, and we get 42. On the other hand, we could first evaluate 3 plus 4, which is 7, and then multiply it by the result of 2 plus 4, which is 6. Again, we get 42. This should not come as a big surprise to you, of course. But what about calling functions instead of just doing basic arithmetic? Consider the factorial function. The factorial function fac, we have seen it before in the lambda calculus, is a function that takes an integer and returns an integer. So fac called on some integer n is defined as if n is 0, then return 1, else return n times fac of n minus 1. An example reduction, fac2 reduces to if 2 equals 0, then 1, else 2 times fac2 minus 1, which reduces to 2 times fac minus 1, 2 minus 1. How could we continue here? We could either continue by going 2 times fac1 goes to 2 times if 1 equals 0, then 1, else 1 times fac1 minus 1. Or we could reduce this to 2 times if 2 minus 1 is equal to 0, then 1, else 2 minus 1 times fac 2 minus 1 minus 1. So we don't reduce the term 2 minus 1 initially and see how we go from there. Reduce it later maybe. Which way is generally better? Feel free to pause the video and think about it for a minute. Which of these reductions would you prefer? Can you give a reason why you would prefer one of them? Think about it for a moment. Two possible evaluation strategies that we can apply to evaluating a program are innermost and outermost evaluation. Consider that you have a program f called on some expression exp. Innermost evaluation first evaluates exp, then inserts the result of exp into the function body of f. This is also referred to as eager evaluation or callable value evaluation. Outermost evaluation inserts exp directly into the function body of f and then evaluates the resulting program. Also, this is called lazy evaluation or call by need evaluation. Of course, we can ask ourselves which one of these is better. Does it even matter? It definitely does. Look at the square function. It's quite simple. Square of n returns n times n. So far so good. If we reduce square of 2, square of 2 by innermost, leftmost evaluation, so we always pick the if there are several innermost terms, we pick the leftmost one. So we reduce square 2 in the first step, yielding 2 times 2. Then we reduce the innermost term, which is 2 times 2, to 4. We then evaluate square 4, reducing to 4 times 4. Evaluate 4 times 4, which is 16. Finally, we can evaluate square 16, and we reach the final result 256 in 6 evaluation steps.